We are. Yes. Thanks so much.
Give me 1 second. Let me mute my phone.
Fair enough. Yep. Well, thanks everybody for joining this wrap-up seminar series with Helix. We're into our second presentation of the first session, and this is being recorded, so we can post it on our YouTube website later. This is our first in-depth use case presentation on the transmission distribution co-convergence with commercial tools. We have a numbering convention you'll see throughout these, where this happens to be called 4.3. And this will be presented by Adil Latif from INRO. We have about 12 minutes for the presentation time, and then we'll have about the same for question and answer while we're all online. That'll try to wrap up a bit before the top of the hour. And then again, we'll reconvene again in another week with the next series. We'll come back to that at the very end. But without further ado, welcome, Adil. Go ahead and take it away.
All right, thank you, Brian. Hi guys, my name is Adil Latif, and I've been leading the T&D co-convergence with commercial tools. I'll try and keep this very quick, just because I've quite a few slides to cover. We've got SIME as a partner on this use case, and they've been really, really helpful. I would like to thank them for their efforts to make sure that this use case comes to a good conclusion. All right, this use case had two main focuses. Number one, we wanted to showcase that Helix can be integrated into commercial tools with little effort, essentially, and it is able to communicate with them, work with them. We're able to make it part of our Helix tools ecosystem. And the second thing we essentially wanted to do was, as our core simulations keep bigger and bigger, keep growing, we wanted to build out a co-convergence helper federate. So each simulator has its own solver under the hood. But when you're exchanging information across boundaries, we've been told that in certain situations, we run into convergence issues. And what we essentially wanted to do here was build out this capability where you could use this co-convergence helper federate and try and converge in these tough conditions. As part of this, we had four main tasks: prototyping the convergence federate, developing the Helix interface for commercial tools. To this point, we built out Helix interfaces for the SIME distribution tool and PSSE. We wanted to do sensitivity testing of the use cases we were building out. I'll talk about that in a minute, and then some insights I'll share from the simulation results that we've done. All right. So for the first piece, the development of the co-convergence helper federate. So the prototype was open sourced a year and a half ago. Sorry, we've come up with a new version, which I'm going to be open sourcing in the next week or so. This implementation would be able to run both loosely coupled core simulation and tightly coupled core simulation. Just for semantics, when I talk about loosely coupled core simulation, what I'm meaning is each time step information is exchanged only one time across boundaries, and then we move to the next time step. And when I'm talking about tightly coupled core simulation throughout the rest of the presentation, I'm talking about iteratively exchanging information until you converge and then moving to the next time step, essentially. This prototype allows us to enable or disable the co-convergence helper federate as well. The way we've set this up is as follows. You see that you've got multiple federates participating in a core simulation. A co-convergence helper federate is essentially an additional federate that is added to the core simulation. It subscribes to every single publication and then publishes a variant of that same variable, essentially, right? What is being calculated by the algorithm. And I'll talk about those algorithms in a minute as well. All right, so how does all of this work? So imagine a very simple core simulation where you've got one transmission and one distribution, right? So this is how information is exchanged. Each iteration or each time step, the distribution would calculate some power, that net power on the distribution is going to be transmitted to the transmission side. It is going to use that, update the load on the coupled bus, and it's going to calculate some voltage, and that is going to be exchanged back. Now, when I add a co-convergence helper federate, what essentially happens is we're adding another federate in between this communication piece, where we'll have algorithms here that is actually going to subscribe to UNS and try and figure out if you're able to use information to co-iterate and improve the rate of convergence, essentially. All right. In our use cases, we chose to use T&D co-simulation as the use case. So the transmission model we've chose to use is two of them. One being a PSSC example model that comes with PSSC bundled with it, and the large use case that we worked with was the Texas A&M synthetic model, which is a 10,000 bus open source data set. I want to point out that we made sure that every data set we use is publicly available, because we do intend to make all of the use cases public along the simulation results along with the data sets themselves. The distribution models, we chose to use the smart DS models just because they've got a lot of variability built into them. They're synthetic, but very close to being real. And they were available for both SIME and OpenDSS. And they're both open source. Both of these variants are available open source, which is why we chose to go with them. All right. Baselining simulation results. So when we started to do this course simulation, what I did was initially just I wanted to try and figure out what is the impact of co-iteration, essentially, right? When I'm co-iterating compared to a loosely coupled course simulation, what is the impact there? So the graph on this left here is essentially just a tightly coupled course simulation. Each line you see here, each trend line you see here is a time step. And what you see is, and this is for 10 different federates connected to a transmission federate, essentially. But what you see, there's two main takeaways from here. One, you converge very quickly. And two, if you look at this error, the error is very small. So what I wanted to very quickly see was what actually is the information gained when we do a tightly coupled course simulation. Can we get away with a loosely coupled course simulation? So the graph on the right here is error averaged across 10 federations, across all federates in a federation, and then all time steps in that federation, essentially. So this is averaged across everything. And what you see very clearly is that the error was between a loosely coupled course simulation and a tightly coupled course simulation was very small to begin with. Now that this course simulation, even when I co-iterate, this converges very quickly. So this wasn't a use case we were interested in, because adding a helper federate here won't make things what makes this interesting, right? Because it's already converging very quickly. So what we wanted to do was actually try and make this a little harder, the use case a bit harder, so that we see a lot more iterations before we start to converge. To that end, we tried a few things. We did a scale testing where we went from one. The way we set up federations, so essentially each co-simulation run, we started to increase the number of coupled nodes on the transmission side, going from 1 to 10 in this example. With SIME, we did scale up to 100 federations as well. SIME, as part of cost share, provided us 100 SIME licenses, and we've scaled to 100 as well. And the results look very, very similar. They were just not very easy to digest, which is why I chose to use the smaller use case for this presentation. All right. One thing that was very clear was one thing I wanted to find out is, as we scaled, did the average residual increase? So the error in convergence did increase. That did not seem to be the case, as you can see here. The second piece I wanted to see was as the size of the distribution federate. So when I'm coupling distribution simulators to the transmission, does the size of the substation actually impact average residual across federate? That did not seem to be the case either. What I will point out is, because you don't see any trend here, right? What I will point out is that one thing I did realize was that federate 1, 2, 3 are geographically co-located on the transmission network. So is this cluster here, and so is this black and blue cluster here. So what I did realize was that there is strong correlation in convergence error, and that is dependent on where you're located on the transmission network. A couple of other things we tried to do to try and increase the number of co-iterations was add distribution controllers. So we added about 900 controllers across 10 different distribution models, capacitors, regulators, and PV with volt-var control. That did not impact iterations a lot. This is E-7, so it's a zoomed in region. And what you can see here is that even with that, we were able to converge very quickly in about 5 to 6 iterations. We changed the type of load, so we thought maybe adding voltage dependency on the loads might impact iteration, and that did not have a big impact either, right?
Quick heads up, we got about 3 minutes left.
I've got 3 minutes left. All right, so I'll just very quickly go through this. We implemented a couple of algorithms here. We were able to get it to converge, but one of the key takeaways here was that if you have a tree-like dependency in your co-simulation, a helper federate is not required. What we then did, and this was interesting results, was we started to mesh the distribution networks together. And once we started to do that, we had circular dependency. Now information is flowing through here, it's flowing through the transmission distribution, and then it's flowing through back here. And now we've got the circular dependency. The sensitivity testing that we did was I scaled on the coupled nodes. So imagine we've got phase A, B, and C. I coupled just phase A first, then phase B, A and B, and then phase A, B, and C. And then also scaled coupled buses, so essentially going from just one mesh net distribution to 2 to 3. And I implemented a lot of different algorithms to test what the impact was. In the first example here, I'm just coupling phase A, but what the key takeaway here is because of the nature of the coupled voltages on a distribution network, as this algorithm brings this voltage together, you see that both these voltages come closer as well, even though they're not part of the problem itself. The second takeaway here is that as soon as I do this mesh network, you see that the transmission network, on the transmission node where you coupled, the iterations do increase considerably, right? That was the first takeaway. So the second question was, as I increase the number of try and couple phase A, B, and C all together, what would happen? One thing I realized was it takes a lot more iterations to converge, but I was able to converge. Not every time though. Convergence wasn't guaranteed. I was able to achieve convergence about 94% of the time. Convergence is a lot harder. It's taking about 10 times the iterations compared to a single phase when I was converging just a single phase. And one final takeaway I'll talk about is that I also increased the number of meshes between the distribution networks. That only added a fraction to the total number of iterations required to converge. So the bigger challenge was to get phase A, B, and C to converge together compared to increasing the number of meshes in the distribution. That seemed to be like a secondary impact on convergence. All right, I think I've already talked about this. And this final graph just wanted to show you that even as you're converging all three, what is the impact on the transmission network itself? Each red dotted line is a time step essentially, and we're able to achieve convergence in every single time. All right. So what is the contribution to this Helix Plus? We showcase the Helix ability to interface with multiple open source and commercial tools. We've open source software. And for example, SignPy is already open source, which is Helix interface with SimDist. This is being used by a couple of universities and the national lab in Canada already. So I consider this a big success. I actually got an email asking for help to set this up just yesterday as well. The co-converges helpful federate. The prototype is already open sourced. I will open source the complete implementation by the end of next week as well. We will open source the convergence use cases as well. So the data that I showed you, how to set this up, and users would be able to run those on their own laptops as well. As part of this effort, we've standardized the Helix interface for already existing tools like PyPSSE and PyDSS. So all new projects going forward are using these standard interfaces. I think Jason already talked about those. We're able to swap between PyDSS and SignPy. The disk transmission doesn't need to know what it is communicating to. So that is one of the biggest advantages. And we've come up with 2 papers. We've had a conference paper, and then we're working on a journal paper that is, I believe, 90% done. We should be done in the next 5 to 6 days. Thank you. Any questions?
Awesome. Thanks so much, Adil. This is really exciting work, and we've got about 10 minutes or so here for questions before we wrap up. I'll also keep an eye on the chat if people have questions in that context. But feel free to just unmute and come on. Or if we start to have a lot of different questions, then you can raise your hand as well, and I can call on folks. It looks like Jason, go ahead.
Yeah, a question for Adil is, obviously I'm excited about seeing us move towards common interfaces and things like that. How challenging was it to use those? Did it, add complexity? Did it actually make it easier in some ways? Can you give us a little bit of your experience in using that?
Yeah, I think yes. It does add a lot of ease of use, especially to new folks who's starting with Helix, right? If you've got the same use case on two simulators, in this case, for example, we had the SmartDS models for both OpenDSS and Sign. If you're able to switch between them arbitrarily, that makes setting up co-simulations very easy and a lot more powerful. I would say there are certain things that do get sacrificed when we're moving towards a common interface, just because all simulators work slightly differently. So there were some pieces that were on the chopping block, I would say. But yeah, I would say 95% of the capabilities are there, just because most distribution system simulators work kind of exactly the same way.
Awesome. I had a quick clarifying question, hoping others will come in as well too. You talked about how it was really interesting to see that more or less if we have non-meshed distribution, the co-convergence helpers unnecessary. Co-convergence still useful, but we don't need any sort of helpers to get that to work. But as soon as it's meshed, that does become really critical. And you highlighted the idea that it's not necessarily the meshing, but also the multi-phases. So I was trying to understand, when you talk about the multiple phases, do you mean getting all three phases to have, say, a uniform voltage because that's what the transmission feder is assuming? Or is there some other piece you have in mind when you're trying to get the three phases to converge?
No, so the main issue is that a distribution system is inherently unbalanced, right? So you might have like three different voltages on three different phases, right? Because I've been using gradient-based solvers. I use gradient-free solvers as well, but they were so terrible with time. I chose not to even show the results, just because they're like at least 10 to 15 times slower compared to, say, Powell or Nelder-Mead, right? So I did use differential evolution as well. I chose not to present the results just because they're kind of useless in this application, at least. What I was alluding to this, so we've got three different voltages here, right? Phase A, phase B, and phase C are all going to have different voltages, and I randomly chose buses on the two different bus distribution networks. That is how I set this up. And when I build out these use cases, I can say, okay, from this bus, which is downstream of the substation, of course, mesh this bus to from this distribution network to mesh to a different bus in a different distribution network. They, of course, here, for example, the voltage here was this on phase A, this on phase B, this on phase C on node A in a different bus on a different network for federate essentially, and it was very different on the other one, right? Now, if I want to mesh them, they need to merge, converge to a single value, right? And that needs to be done across all three phases. So if I just converge phase A, it's a much easier problem to solve. But because phase B and phase C voltages are coupled to phase A, just because of the nature of the distribution network, you see them moving, even though the algorithm isn't even looking at these variables. I just plotted to show you that the impact is, as you do this, it's going to help bring the other two closer as well. Now, this tiny gap, if you want to close this gap as well, and you want to make this part of the problem as well, try and converge these two as well. Now, this becomes a very difficult problem to solve, because here, if you look at this, I was able to get this to converge in about 60, 70 iterations. The same thing when I try to converge phase A, B, and C now, which is all three phases together, it takes a lot longer time. And this is average convergence error across all federations across all federates across all time points, essentially, right? You see these large jumps here. This is because some simulations did not converge. Load model 1, model 2, model 3 represent constant power, constant impedance, constant current, which did not have a big impact. And having or not having controllers, even discrete or continuous controllers like volt-var or regulators, did not have an impact on convergence, a significant impact on convergence as well.
Well, no, that's very helpful. The trick is not the T and D interface, but those D to D interfaces between the different distribution
Yes.
federates. That's very cool. Thanks for clarifying.
That seemed to be the much tougher problem to solve, in my opinion, especially because I was using gradient-based algorithms. I did have an implementation with a Newton-Raphson solver, but the results looked horrible when I was looking at them yesterday. I think I made a mistake somewhere. I'll have to figure that. I used forward finite difference to estimate the Jacobian. I think I made a mistake somewhere because the results looked horrible. I will take a look at what went wrong there. But yeah, I just showed you the results for the gradient-based solvers.
Awesome. Well, thanks so much. Thanks for the clarifying. I don't see any other questions currently in chat, but definitely excited to have some. Yep, looks like John Gosh may have one. Fantastic.
Yeah, I make one comment is that you know, I really like this presentation. I'd encourage you to include results that didn't work out, because I think that many times people ask the question, you know, is what's the performance hit you take, for example, to go from a gradient-free method to a gradient-based method. And so so include things that didn't work to the extent that's reasonable, because that'll tell people directions that they shouldn't go. Thanks.
Yeah, I will take that into account. And yeah, for the paper, we're doing that. I thought I had just 12 minutes, I was told. So I was trying to figure out what to put here and what not to put here.
Got it.
Great, thanks. Great point, though, for sure, there, John. Other questions from folks for Otto? We've got a couple more minutes left, so probably time for one more question, maybe two.
I'll put one question out there. Could you elaborate on the interest from Natural Resources Canada?
Yeah, so they've been using SIME for a while now, and they were interested in doing co-simulations for their studies. And then they reached out to me a while back, actually, and I've had a couple of meetings with them. They wanted to get an overview of SimePy, and then they wanted to figure out how to get it to work, which I had a session with them trying to set that up, and that was a while back. But since then, I've had a couple of universities. Even yesterday, I had an email pertaining to some interest in SimePy.
Excellent, thank you.
Yeah, definitely very exciting. Other questions or comments to share? We've got time for one more, probably. Well, not hearing any, and certainly encourage you to follow up with Otto offline. You see his email there in the slides. I'm going to go ahead and put back up the schedule, the upcoming schedule for future weeks, and then we'll go ahead and wrap up. And so, first off, please join me in thanking all of our presenters today. First of all, thank Otto for the great presentation around the T&D co-convergence with commercial tools. Also wanted to thank Jason for the overview, and Chris and Guoyi for the great context setting and the overall comments for this exciting project. As we look ahead, here's the upcoming schedule of presentations. Again, these are going to be every week for the next 5 weeks beyond today at the same time. And next week, we'll hear from Anantha, who's one of our industry partners at NRECA, talking about integration with their open modeling framework, as well as perhaps some other aspects of some great work they've done in a use case together. And then we'll also hear from Phil on a lot of the core development pieces. You saw some previews of that in Jason's slides earlier today. And but we'll have a little bit more in depth, and as always, just like today, a chance to answer questions after each of those presentations. And then as you look ahead for the following weeks, we have more use cases. And then towards the end, we get the excited updates around the multi-lab capstone demo, as well as around standard interfaces and next steps for Helix. Also wanted to quickly highlight that I will not be around to be the MC next week. So thanks to Jason for stepping up to be the MC next week. I'll be back again on March 2nd. So last call for any questions or comments before we wrap up. Additions, of course, from the team. Awesome. Well, thanks everybody again for joining. It's very exciting. I think at one time I saw close to 50 people here, so excited by those numbers, and hoping, just to be clear, this is open for anybody. Presumably people who are interested in using Helix or RDR might be the most relevant, but feel free to forward this series invite widely and invite any of your colleagues or students or others who might be of interest. We're also always looking for feedback. I know a number of our TRC members have been able to join. Thanks so much for your support over the years, but also if you have any comments or questions, feel free to send us an email in that space. With that, we'll go ahead and wrap up. Thanks so much, and we'll see you again this time next week.
Thanks, everybody.
Thanks.
Thank
Thanks
you.
again for coming.
Thank you.